So far this module we've been talking about different ways in which we can model dependencies in time and over space for stochastic processes. We started in chapter 2 by looking at HMMs, so these model dependencies in time, and we derived estimation techniques for data which was assumed to arise from a HMM. The basic recipe there was that at the lower level we had a Markov chain, and that captured all the dependencies over time. And then above that, conditional on that Markov chain, which is unobserved, we had conditionally independent observations, which were the things that we could actually record. And the objective there was to try and recover that unobserved chain underneath we only kind of observe by proxy through the observations. And then what we did was we moved on to building up a spatial process over a spatial domain. So we began with a lattice and then eventually ended up with graphs. And what we saw that it was a little bit more difficult, right? So we had to make an appeal to the Hammersley-Clifford theorem. We had to think about things in a divide and conquer way. But what we saw eventually was that Markov chains were subsetted within these constructions. So our objective in this chapter is to start thinking about how we could use these spatial processes in applications. And so these are ubiquitous now. So all of these kind of geospatial applications of statistics rely on these kinds of methods. So I suppose the thing to keep in mind is that the whole idea here is the same idea as what we've been using for HMMs in time, right? So here I've written down the definition of the HMM in time. So the YTs given the XTs are conditionally independent, and they come from some parametric distribution which is parameterized by a parameter depending on the state of the chain. And then the XT comes from a Markov chain, which is parameterized by some initial distribution pi and a one-step transition matrix P. So the only difference now in going from HMMs in time to HMMs in space is that instead of T indexing a time, which is ordered, T indexes a site in a domain. So that might be one site on our lattice, or it might be some site geographically. And then we say that the XTs within that domain, which we'll just call D for a moment, then they follow a Markov random field, which are parameterized by which is parameterized by some parameters. Okay, so what we do is just kind of draw a graph of that, and maybe compare the graph for the HMM in time versus the HMM in space. And we have here on the top level, so these are going to be what's going to result in our observations. And so on. On the bottom level, we have the Markov chain. And the Markov chain captures the dependency over time, while the Y's are the things that we observe. Now, what I want you to do is pause the video and try and draw the corresponding graph for a hidden Markov model in space. Okay, welcome back. Well, we keep it simple for the moment. Let's think about our lattice. What we have is different sites on the lattice, and they obviously, so depending on the nearest neighbor system, they're going to depend on their neighbors if that's the system that we use. And then we'll make observations at each of those sites, right? And it's the observations that's going to give us the information to learn about those sites. So again, we have our Y's, but this time each Yi is attached to a site, Xi, and that depends on its neighbors. So in the case of the hidden Markov model in time, we know that the conditional independence graph actually looks like this. And so the time slice is like almost taking one row of this lattice. Yeah. And we can sort of think, so it's sometimes instructive to think in this kind of superset and subset way, in that time is a special case of the space where space is collapsed to only being allowed to evolve in one dimension. And in that case, we can enforce an ordering. Okay, so what we're going to do now is discuss one of the kind of key applications of Markov random fields, and this was one of the very early applications, but it's really interesting, and it's about image denoising. So effectively what we have here is a sort of a photograph or a picture or something, and we imagine that it becomes corrupted by noise. This could be to do with any number of reasons. So it could be to do with the picture being old and you want to kind of reconstruct it in some way, or it could be due to communicating the picture and there's some kind of corruption due to the communication, right? So you can't communicate perfectly and errors are going to be introduced. So how do you reproduce the picture at the other end with minimal errors? So how exactly do we digitally represent pictures? We'll take this drawing of a cat. This is what we call a binary image because it's made up of either black squares or white squares, and each of the little squares that's in the image is called a pixel. So there's 366 pixels along the rows and 270 pixels along the columns. And we'll associate 0 with the white pixels here and 1 with the dark pixels. This can be obviously represented as a matrix, this image. And in terms of kind of color spectrums or shades, this is the simplest picture we can get because there's only two shades included, right? So there's 0 or 1. In general, a grayscale image, which is what we'd know as a black and white image, that will have a range of shades of grey from 0 being the closest to white and 1 being the darkest, usually in about 256 steps. And often how we'd represent that is as a matrix of values between 0 and 1. And then if we go to color images, that's usually represented, so each pixel is represented as a triplet of colors, an RGB triplet, telling us what mixtures of red, green and blue each of the pixels are. In those terms, a color image would have 3 channels of color, whereas a grayscale image would have just 1 channel of color. So how do we, so this is how we can kind of represent images. If we're talking about storage, if it's a grayscale image, we can store it just using a single matrix. If it's a color image, we need a tensor, so like a stack of 3 matrices stacked beside one another, one for the red channel, one for the blue channel, and one for the green channel. So what we're going to do now is think about corrupting this image with noise. And in this case, because we're dealing with a simple image, which is composed of either zeros or ones, 0 for the white pixel and 1 for a dark pixel, what we're going to do is randomly flip the pixels with probability 0.1. And we'll do that independently over pixels, right? So we're going to change this clear image into a noisy image, and the noisy image is what we could imagine as being the corrupted image, right? So we communicate the image and at the other side some corruption has happened to the image and we get a noisy version of it and we want to clean it up. Let's think about how we would actually kind of represent this notationally. Right, well, we can see that our pixels here are arranged along a neat grid, right? So that suggests to us that we could use a lattice. And what we could have is we could have a site on the lattice corresponding to a color. of white for 0 and black for 1. And okay, so if we set things up like this, then well, what we'll have is 366 by 277 nodes in our lattice, and then each of the nodes can take a binary value, right? And if we think of it kind of representationally, right, so we're looking at this image now, what kind of characterizes this image? So if we were to describe it in a spatial sort of way, well, we can see that, okay, the density of black pixels, that represents the outline of the cat. And so where we have black pixels, we tend to have black pixels in the neighbors around that. And similarly, the white represents the rest of the space, so the internal part of the cat and the border outside it. And indeed, where we tend to have white pixels or pixels of value 0, we tend to have the same in the neighbors. And this should start reminding us then of our autologistic model, right, where we get these clusters of zeros or ones spatially. To formalize our discussion, let's think about it like this. So we're going to let x represent the actual value of the pixel in each case, right? So 0 or 1. So x1 down to x capital N. N is equal to n times m, where n is the row dimension and m is the column dimension. So we have n times m pixels. Okay, and then how do we add noise? Well, what we're going to do is we're going to take each pixel independently and flip its value or not. And we're going to flip its value with a probability of 0.1. And what we'll do is we'll call the noisy image y. So we'll have, for each pixel in our noisy image, we'll call the pixels yi. We'll have yi is equal to the actual value of the pixel xi with probability 0.9. or 1 minus theta, and it'll be equal to 1 minus xi with probability theta. So we go through each of the pixels in turn and we flip them with probability 0.1 independently. And what that gives us then is our noisy image, which we denote by y. And what does that noisy image look like? Well, it looks something like this, okay? And what we see is this sort of grainy sort of pattern, which is induced by flipping the values of the pixels. So we'll denote the noisy image by y1 up to yn. Again, it has the same number of pixels, and but it's just a corrupted version of x. So the question is this. Okay, so supposing you received this image in some kind of digital way, and you wanted to figure out how to kind of recover the image in as much fidelity as possible to the one which was communicated at the beginning. And so what you want to do is figure out some way to denoise the image, right? To do that objectively. And we could use this observation that nearby pixels tend to have similar values, right? So if I'm in an area which codes the outline of the cat, my pixels will be 1 and I'll be surrounded by 1s. And if I'm in an area which encodes the border, then the pixels will be 0 and they'll be surrounded by 0s. So when we receive the image, we see y, but what we really want to do is recover what x was before the image was sent. So whenever you're ready, go over to the next video and we'll discuss how to do that.